Deep beneath the Pacific Ocean's surface exists a place untouched by sunlight, nearly 6,000 meters down, where temperatures plunge toward freezing. The ocean floor drops away into an enormous underwater canyon. This is the Mariana Trench, the deepest point in Earth's oceans. Here, in perpetual darkness, the sun's warmth has never penetrated. Pressure reaches over 1,000 times what we experience on land, capable of instantly crushing any vessel not built to withstand it. For years, scientists believed nothing could possibly survive in such extreme conditions. They were wrong. Today, we're diving through every layer of the ocean. From the warm, sunlit shallows teeming with life, all the way down to the most extreme environments on the planet, where survival requires extraordinary adaptation. Our journey starts in the epipelagic zone, the sunlit surface waters, extending down about 200 meters. This upper layer is the ocean we know best. It's where we fish, sail, and observe marine life most directly. Here the ocean pulses with light and movement. Sunlight penetrates deep enough to fuel photosynthesis. Microscopic organisms called phytoplankton float with the currents, forming the foundation of the entire ocean food web. Like plants on land, they capture sunlight and convert it into energy, earning them the nickname grass of the sea. Though invisible to the naked eye, phytoplankton exist in staggering numbers. They feed krill, tiny shrimp-like creatures, which in turn feed larger animals, fish, seabirds, and whales. It's a simple yet powerful cycle that sustains life in the upper ocean. But as we sink beyond the sun's reach, where photosynthesis becomes impossible, the ocean transforms completely. Welcome to the mesopelagic zone, the twilight zone. Stretching from 200 to 1,000 meters deep, this layer marks the transition between the bright surface and the darkness below. Sunlight here is weak and scattered. The ocean fades into deeper shades of blue. Warm colors, reds, oranges, yellows, vanish first. Their longer wavelengths get absorbed quickly, leaving only short blue wavelengths that can travel deeper. The water grows colder. Pressure steadily climbs. To survive this dim world, creatures have evolved remarkable abilities. Up to 80% of animals here produce their own light through bioluminescence, specialized chemical reactions within their cells. In a place without sunlight, this ability becomes a survival tool. Lanternfish emit a soft glow from light-producing organs on their bodies. By matching the faint light from above, they become nearly invisible to predators below, a technique called counter-illumination. Other creatures use light as a weapon. The anglerfish, with its iconic lure and razor-sharp teeth, dangles a glowing bait to attract prey. When something drifts close enough, its jaws snap shut. Some fish flash gentle pulses of light to communicate with their own species. But bioluminescence isn't the only adaptation. Many species have evolved enormous eyes, capable of detecting the faintest traces of light, allowing them to spot prey drifting above or predators rising from below. Others rely on color. Some creatures have evolved completely transparent bodies, allowing light to pass through them rather than reflect back. In the faint blue twilight, this makes them almost impossible to see. As we descend further into the lower twilight zone, we encounter one of the strangest creatures on Earth, the siphonophore. At first glance, it looks like a single jellyfish, stretching meters into the dark water. But closer inspection reveals something far stranger. A siphonophore isn't one animal. It's a living colony made of thousands of tiny, genetically identical individuals called zooids. Each zooid has a specialized role. Some have stinging tentacles to capture prey. Others defend the colony. Some exist solely to reproduce. Alone, these organisms would struggle to survive. Together, they function as one unified life form. Their water-filled bodies provide neutral buoyancy, allowing them to withstand pressures over 80 times greater than sea level. In a region where food is scarce, energy must be conserved. Siphonophores don't rely on speed, they rely on efficiency. As we approach 1,000 meters, the last traces of light disappear completely. We've entered the bathypelagic zone, the midnight zone. This marks the point of no return. Sunlight cannot reach here. The ocean exists in complete, unbroken darkness. Water temperature drops to an average of just 4 degrees Celsius. Stretching down to nearly 4,000 meters, the midnight zone remains largely unexplored. The crushing pressure makes it one of the hardest places on Earth to reach. At 1,000 meters, pressure has risen to about 101 atmospheres, 101 times stronger than the surface. At sea level, we live under 1 atmosphere of pressure from the air above us. But water is much denser than air. The deeper you go, the more water stacks above you, increasing pressure with every 10 meters. Submarines and cameras require thick hulls and reinforced materials to avoid being crushed instantly. Marine life has adapted too. Deep-sea creatures can't have air-filled spaces like lungs. They would collapse. Instead, they've evolved soft, flexible bodies made of jelly-like or watery tissue. Since liquid is nearly incompressible, they don't get crushed. Most lack the air-filled swim bladders common in shallow water fish. Instead, they use low-density oils or fats that can't be compressed. Most fascinating, within their cells are special molecules called piezolytes. These compounds act like support beams, preventing cell membranes and proteins from collapsing under extreme pressure. Here, in near total silence and eternal darkness, life continues, just on different terms. In the midnight zone, there's no sunlight to fuel plants, no algae forest to start the food chain. While some creatures actively hunt, others take a quieter approach. Instead of chasing scarce prey, they wait for food to drift down from above. Scientists call this marine snow, a slow, continuous rain of tiny fragments, dead plankton, mucus, waste, and organic debris sinking from the sunlit surface. But it's not abundant. By the time it reaches the midnight zone, it's sparse and scattered. Every fragment counts. Life here moves at a different pace. Animals grow slowly, reproduce infrequently, and live much longer than their shallow water relatives. Survival depends on patience and remarkable adaptations. Some possess enormous mouths. The gulper eel has jaws that open so wide it can swallow prey larger than itself. Its unique jaw can expand 3 or 4 times its body width. The black swallower can consume prey twice its own length and 10 times its weight. After swallowing a massive meal, its stomach stretches so extremely it becomes nearly transparent. In a place where food is scarce, it may endure long periods without eating. Camouflage is another powerful tool. The stoplight loose jaw produces faint red light to illuminate prey. Most deep-sea animals can't see red, so the loose jaw shines its beam like a private flashlight, revealing unsuspecting prey while remaining invisible to them. In the midnight zone, some creatures are exceptionally large compared to shallow water relatives, a phenomenon called deep-sea gigantism. From the armored giant isopod crawling across the seafloor to massive sea spiders with legs stretching up to 2 feet, the forms here are both fascinating and terrifying. But one stands out, the giant squid. For most of history, it was legend, sailors' tales of enormous tentacles stretching over 20 feet. These stories were dismissed as exaggeration. Then in the 19th century, Danish zoologist Japetus Steenstrup confirmed the species after analyzing a massive squid beak. Decades later, Moses Harvey acquired giant squid remains caught in a fishing net off Newfoundland. He sent the preserved specimen to New Haven, Connecticut, where scientist Addison Emery Verrill studied it. Working with artist James Emerton, they produced the first detailed scientific description and created the first accurate model, a plaster reconstruction over 30 feet long. Since then, scientists have collected around 50 complete specimens. From these remains, we know giant squids can potentially reach 60 feet in length. Why do creatures grow so large in the coldest, deepest parts of the ocean? Several factors work together. Food scarcity favors larger bodies that can travel further and store more energy. Cold water slows metabolism, allowing gradual growth over extended lifespans. Fewer predators mean organisms live long enough to grow larger. High dissolved oxygen levels may also support larger body sizes. Far below even the giant squid's realm, the seafloor opens into a vast expanse, the abyssal plain. At depths of 4,000 to 6,000 meters, this part of the ocean is called the abyss. The terrain is almost completely flat, stretching thousands of miles and covering roughly half the planet's surface. Temperature hovers around 2 degrees Celsius, sometimes dropping near 0.5 degrees Celsius. No sunlight, no warmth, only darkness, pressure, and stillness. It remains one of Earth's least explored regions. At its deepest, pressure climbs to nearly 600 atmospheres, 600 times stronger than the surface. From the few missions that have reached it, we know it hosts creatures found nowhere else. Among them, delicate tripod fish, standing motionless on long fins, slender rat-tail fish gliding above the seafloor, and various species of squid and anglerfish moving with deliberate precision. Food is even scarcer here. Most nourishment comes as marine snow, but by the time it reaches the abyss, little remains. Life is sparse, small, and slow-moving. Occasionally something extraordinary happens. A whale dies, and its body sinks to the seafloor. This whale fall brings sudden abundance. Scavengers feed on soft tissue for months. Smaller creatures settle into sediment enriched with organic matter. Even after the flesh is gone, bacteria within the bones break down stored lipids, releasing sulfides that provide energy for specialized microbes. This process can support a thriving community for decades. The Hadal Zone begins at 6,000 meters and descends to an astonishing 11,000 meters at the Challenger Deep in the Mariana Trench. Though rarely observed, this realm represents 45% of the ocean's vertical depth. Here, the environment approaches the limits of what life can endure. Temperatures hover just above freezing, but the greatest challenge is pressure. At 10,000 meters, the weight of water presses down with over 1,000 times the force at sea level, capable of crushing the very structure of living cells. The Mariana Trench lies in the western Pacific, about 1,550 miles east of the Philippines. This scar on Earth's crust resulted from subduction, the Pacific tectonic plate slowly slipping beneath the smaller Mariana plate. Over millions of years, this immense force carved a long V-shaped depression. The deepest part, the Challenger Deep, is a slot-shaped valley within the trench floor. In 1960, Swiss engineer Jacques Picard and U.S. Navy officer Don Walsh descended into the Challenger Deep aboard the bathyscaphe Trieste, reaching nearly 11,000 meters. In 2012, filmmaker James Cameron made a solo descent in the deep-sea Challenger submersible. Life observed here consists mostly of small, resilient organisms and microbial communities. Scientists have documented simple invertebrates, shrimp-like crustaceans adapted to extreme pressure. Many appear translucent or pale. Research suggests they produce a special aluminum-based gel that strengthens their exoskeleton. We've reached the deepest point on the seafloor. We've measured its depth and observed life thriving under impossible conditions. Yet we still know so little. Much of the seafloor remains unmapped. Vast regions have never been seen by human eyes. Future discoveries will depend on robotics, remotely operated vehicles, and underwater drones that can dive more often and stay longer than any human crew. The deep sea holds clues to Earth's climate, tectonic movement, and how life endures in the harshest environments. For now, so much remains unseen. In the endless darkness, entire ecosystems, unfamiliar species, and unknown processes likely wait for discovery. The question is no longer whether we can reach these depths, but what we'll find when we do. If you want more stories where exploration, science, and mystery meet, subscribe to Compass of the Earth. Be the first to see what lies hidden in the deep.